So today we are going to talk about the experiment on finding the index of refraction of glass and also the index of refraction of water. And this is called Pfund refraction. Pfund is the name of a American scientist, physicist who developed this method. In order to do that, we have a piece of glass, as you can see in here. And here's that glass in here. And what we are doing, we are shining a laser just perpendicular to the glass, which I'm going to show to you, or you saw it, or I'll show it to you again later. So the laser shines this light and goes in here. We made the surface below, the part of the surface which is below the glass, we made it to be rough by putting some white paint in here so that we can get a scattered reflection. So now the ray that comes completely normal hits this surface in here, and that's maybe very smooth, and so the reflection would be on itself. But because there is serrations in here, there's some roughness in here, there are other part of this bottom surface that would reflect the ray in different directions. And so one of these rays would be this ray in here. This is coming in here, and it's going to come from glass to the air. So it's going to refract like that away from the normal, because it's going from a optically thick material to an optically thin material. Other rays are like that. This is another one, goes like this. And as you can see, if the angle of incidence becomes bigger, the angle of refraction, which is these angles in here, they also become bigger. Eventually, there would be an angle of incidence, which we call it theta c for critical angle, which is in such a way that the angle of refraction becomes 90 degrees, as I have shown it in here. So it comes in here and basically goes parallel to the surface of the glass. Any ray with higher angle of incidence, such as this ray, is going to be within that range of total internal reflection. And so the ray is going to come back to the glass. Anything after that is going to do the same thing. And therefore, if you're looking from the top view, this part has been illuminated by this internal reflection. This part is kind of stays dark because nothing is reflecting back in here, or the rays that came in here, they refracted and went to the air. So you will see that there will be a dark area. Of course, this is circular, so from here to here, you're going to see a circular black area, and that's what we are going to measure. We measure this diameter. We also measure carefully the thickness, and then by the equation 2 in your manual, you are going to get the index of refraction of the glass. Please note that, as I've corrected in the manual that I'm going to upload for you, these are, maybe there's typos in there in your lab manual, but these are the correct ones. So this is the diameter that you measure on the diameter of the dark circle that you measure, and thickness is what we measure with the caliper vernier. So that equation gives you the index of refraction of glass. Now, in order to find the second part of this experiment is to find the index of refraction of water. So what we do, we use the same glass that we already measured its thickness, same laser, everything, and we just slightly wet the surface of the glass. So we have a layer of water, which I have exaggerated how thick it is just to show you, but there's a thin layer of water right on the top surface of the glass. Same thing happens, but except that this time we have two types of internal reflection. One happens at basically this interface in here. So ray is coming from the bottom part of the glass, reflecting from here, and goes from glass to water. And glass has a higher index of refraction water has a lower index of refraction. So again, the refraction angle is going to be away. It's going to be the ray is going to refract away from the normal, and they come in here and go out, just like they did in here. Well, of course, again, there is a angle of a critical angle that after the ray has refracted in glass, now it is in air, I'm sorry, it has come in the glass and now it has refracted in air, it needs not to get out and go into the air. But this angle is in such a way, just one of these rays is going to have this angle such that this angle is just exactly equal to the critical angle of refraction, I'm sorry, between water and air. So right here at that interface, the ray is going to come back. So any angle before that, the rays would have gone into the air, but at this particular angle, which gives this angle to become critical angle between water and air, the ray is going to come back into the water and then it's going to come back into the glass. And so we are still going to have a dark circle in here whose diameter is going to be, by the way, is going to be different than what we had in here, because in here we had the interface between glass and air, whereas in here we have the interface between the glass and water. So that would be completely different diameter. But anyway, that's not the important thing. The important thing is this, that for other rays that is still going into the glass, there will be, again, a critical angle, which I should have shown in here, and that is the critical angle between the glass and water, which is this angle. So that's theta critical between glass and water. And so when this ray comes in here, because this angle is exactly at, and anything beyond that is more than the critical angle, the ray are going to come back into the same environment. And so it's going to hit this in here, and therefore it's going to illuminate this point. Anything with larger angle also is going to come back into the glass. And so when you're looking at it, you're going to see two circles. One dark circle, just like before when we had only glass, with a different diameter, of course. And then we have another circle with bigger diameter, which happens between. Okay, so I was explaining that we have gonna have two circles, one darker circle like before, and then another dark with larger radius, which is also dark, but beyond that is gonna be illuminated because all these return rays, they are also coming back into the glass. And what we need to do, we need to find or measure this diameter. That's what we need. And we're going to call that D again. It's hard to see the whole diameter when you're doing the experiment. So we are going to measure the radius of that, and this is what you are going to do. And once you got that, you plug it into this equation, and that gives you the index of refraction of water. Please note that this is the index of refraction of glass. Do not use the one that you found in here because this probably is erroneous. Use the one that you have for glass, which is about 1.5. And then from there you can find the index of refraction of water. Please make sure that the diameter that you put in here is the diameter of the larger circle, not the one that is darker and smaller. That's basically it. Now, the only thing that I want to explain for you is that what is the uncertainty in your measurement. There is some uncertainty in measurement of the thickness, either in this equation or in this equation. You see thickness appears. There is some uncertainty in measuring the thickness, and that is delta T. Okay, and remember that the resolution of caliper vernier is 0.01 millimeter. That is basically the minimum uncertainty, so we can use that, but there's other ways that you can estimate it, but at least it's that much. And so we can find in the first part in here, because of the uncertainty in thickness and uncertainty in measuring the diameter of that circle, we have some uncertainty in measuring n. This is called error propagation, as I discussed for you before. To find n maximum, you use this equation, because you want to make sure that these numbers are maximum. So you put the maximum value of d, that will be d plus the uncertainty of d, plus the maximum value of t, which is thickness plus uncertainty of measuring thickness. And to make this maximum, diameter must, the denominator must be the smallest. So in the diameter, you put d minus the uncertainty of the diameter to make this whole fraction the maximum. For n minimum, we do the other way around. So diameter minus the uncertainty, t minus the uncertainty, but the denominator d plus the uncertainty, and that gives you n minimum. Find the average of those two, and that becomes the nominal value. That's what you're going to use to report what is the index of refraction of glass. And as far as the uncertainty in n is going to be this number minus this number divided by 2. And so basically your n is going to be equal to this nominal value that you found from here, nominal value, plus or minus uncertainty in n that you find in here. You do exact same thing when you are calculating the uncertainty of n prime. So again, you look at this equation that gave you n prime, and you want a maximum and a minimum, just exactly the same procedure. Once you found this, you find the nominal value or the average nominal value for the index of refraction of water, and then this would be the uncertainty of that number. So again, your n prime of water is going to be n prime, that's nominal value, plus or minus delta n prime. And then the last thing that you have to do is you want to do a one-dimensional graph. Here is your n value. This is just for glass, and you do the same thing for water separately. This is n nominal value for glass. This is n plus delta n, and here is n minus delta n. So that's the range of the uncertainty of measuring index of refraction of glass. And you know that depending of course what glass it is, but for this regular glass, the book value of n is about 1.5, as I wrote for you earlier. So you can also show where is the book value on this one-dimensional axis. So maybe, hopefully, it falls within this range of your measurement. If it is outside, it is possible that your book value falls outside, but then in either way, I want you to discuss the sources of error. That's all.